Okay, the recording has started. So let's start anyway. Um, any questions?
Sir, I have one question regarding the assignment.
Yes, go ahead.
Yeah, so there was one problem where like we need to find the balance condition of an AC bridge.
Which AC bridge? There were
Uh,
two AC bridges.
the first one, the simple.
First one, right? Yeah.
Yeah. So so could we keep the answer in the form like if we do the calculation of Z1 times Z4 equals to Z2 times Z3.
Mhm.
Yeah, then we get some conditions, and so could we keep the conditions for omega, like we get the condition for omega, something on the omega square and something on like the ratio of the capacitors. So could we keep this in that form, or do we have to like substitute back in R1 and C1 and then present the answer?
Well, look, there are infinitely many ways of reordering or rearranging those solutions. And there is really no good way unless you know exactly what you're looking for. Depending on the particular application you have in mind, for example, if that particular bridge were used to measure capacitances, the ideal form in which the answer should be given is C is equal to something. Okay. However, in the absence of any such information as to exactly why you are going to use this bridge, any form is suitable. But in most cases, there is one form which is easier than the others, and you should be able to recognize that. But in case you are not able to decide whether this form looks better or that form looks better, just leave it at any form that you have got. As long as it's correct, then it's fine. Well, if I had said, how would you use this particular bridge to, say, determine an inductance, let's say? Not that one, perhaps, but then, of course, the question would be, how would you express inductance in terms of the other parameters? But since we have not said anything of that kind, just giving the two balance conditions in whatever form looks convenient is fine. Now, if there's some obvious simplification, like say you have RC plus 2 RC and you have not replaced that by 3 RC, that of course is bad. But other than that, anything else is okay.
Okay, sir.
And in all such cases, it's basically you who have to decide. That is, uh, if we have not completely specified exactly what I want in the question, it's up to you to decide what would be a good way to go about it. For example, I have said something. I've given you something like plot the characteristic curve, the dynamic characteristic curve for a diode. I don't remember, but I am pretty sure that I did not tell you the voltage range that you should use or things like that. That is something which you have to decide. Okay, and I'm pretty sure different people may make different choices, but there's some natural choice to be made, some natural range of choices. So if somebody suddenly plots the dynamical characteristic of a diode for up to say 200 volts, that's fine, I guess, but that will not really give you much information. Can you please discuss the seventh problem in the fourth problem set? You mean the square wave thing, right?
Yes, sir.
Yeah, what do you want me to do? Do you want me to solve the problem for you, or do you want me to tell you how the problem goes?
How the problem goes. Actually, even the hint is not clear.
Okay, was there a hint? What was the hint? Could you just remind me?
It was said that sine wave, no, this square wave is a sine of many sine waves. Sorry, sum of
Hmm?
many sine waves.
Yeah. So that was the hint, but I'm pretty sure most of you know this, right? Haven't you ever studied Fourier series anywhere?
I know this, but how is it relevant here? I didn't get
Okay,
that.
how is that relevant here? That, of course, is a good question. So let's just talk about this. First of all, I'm not going to talk about that particular problem, but in general, any of these circuits, they have well-defined responses for a given. So VO by VI, when we calculate that, we essentially get something like 1 by 1 plus j omega or jq times omega by omega 0 minus omega 0 by omega. At least if this is a resonance circuit, typically this is the kind of form you're going to get, right? Now, you might of course get different forms depending on different kinds of circuits. But what is important is that these values that you have got, the VO by VI ratio, that's for a particular omega, right? Particular frequency. And that actually implies that you're assuming that the input is sinusoidal. Only if the input is sinusoidal with a definite frequency will this expression make sense. Otherwise, this expression simply doesn't make sense, right? Is that okay so far? Yes? Okay, fine. So now, this is definitely true for one particular sinusoid, but what we are asking for is a square wave, right? And that's not a sinusoid. So you cannot directly use this result for VO by VI to tell you exactly what the output is going to be. You can't just plug in the frequency of the square wave in this formula and expect that to give you the correct VO by VI ratio. Okay. This formula works only for sine waves, not for square waves. So the frequency there is not the frequency of the square wave, it's the frequency of the component sine waves which make up the square wave. So I'm pretty sure all of you know this, that basically this will look like some constant into sine omega t, where omega is a fundamental frequency. Then you will have sine 3 omega t by 3 plus sine 5 omega t by 5 and stuff like that. That's a Fourier expansion of f of t, right? The square wave. This also should be pretty familiar. Now, each of these terms have a definite frequency. And what this is telling you is actually what a frequency omega will produce as an output. So, for example, a sine, instead of looking at a sine omega t, I can actually think of this as a to the I omega t plus, say, j omega t, because I'm using j. Say I can think of this in this form, right? Basically, real part of this. And then the important thing is each of these have a definite frequency. This one has frequency omega, this one has frequency 3 omega, the next one has frequency 5 omega, and so on. Each of these has a definite response, right? For example, if omega is close to omega 0, then the omega term is going to give you a large response. But the 3 omega, 5 omega terms, these are going to be suppressed. Is that clear? That's exactly what this response does, right? It has a peak at some omega 0, and when you're moving away from it, the output is small. Now, the important thing is that your circuit is a linear one. So if you give it a sum of lots of terms like these as input, the output will be the sum of corresponding outputs. Sine omega t has a well-defined output. All you do is put in the frequency omega here and you get the corresponding output. Sine 3 omega t, for that you have to put in 3 omega here, you will get the corresponding output. 5 omega here. Okay? So each one of them gives you a well-defined output. So what you need to do is actually find out each individual output and add them together. The next question, of course, would be that there are infinitely many terms here. So how is it possible to add all of them together? The answer is you don't need to. After all, the terms get smaller and smaller as you go to higher and higher harmonics. And also, this response is very sharply peaked at close to omega 0. So basically, omega 0 and its nearby frequencies that will be picked up. Is that making sense? Yes? Or okay, let me just put it this way. Let's say our tank circuit has an omega or f0. Let's say the frequency, I'm just quoting the frequency here, of 1200 hertz, let's say. And my square wave has a frequency of say 900 hertz. So this is the f. Now if the square wave has a frequency of 900 hertz, then it actually has 900 hertz in it. It also has 2700 hertz in it, also has 4500. In fact, all multiples of 900 hertz in it. Okay. Now, each and every one of these frequencies which go up and make up your square wave, they are actually all rather far away from your 1200 hertz peak frequency. As a result, the overall output is going to be very small. Now, suppose I keep on changing the frequency, say I keep on increasing it, and I get close to 1200 hertz for F. So F increases until it gets close to 1200 hertz. Can you tell me what the output will be like? What will the output look like now? You have put in a square wave to an tank circuit, maybe this circuit. And you're looking for the output. So maybe you're looking at the output using a CRO. So when your frequency, input frequency is close to this 1200 hertz peak frequency, what will the output be like? Shivam is saying
More
square wave.
more like a
Anybody else?
sine wave of
Sinusoidal wave.
yeah, of 1200 hertz. More like a
It will
sine wave of
look
1200 hertz.
exactly. It will look like a sine wave of 1200 hertz. Basically, because the 1200 hertz component will almost go through in its entirety. The other components, say the 3600 hertz component or the 6000 hertz component, the multiples, they are so far away from the resonance that they will hardly show up. So basically, your output will look like 1200 hertz. And not only that, what will happen is as you keep on tuning your frequency across this 1200 hertz range, that is, you start from below 1200 hertz, you get close to it, then you cross it and go to the other side, your output will suddenly grow to a large value when f is 1200 hertz and then fall again. But that is what would happen in a standard resonance experiment. I'm not sure whether you have at all had a chance of doing a resonance experiment in a lab. But if you have, you would easily know that as you cross that frequency, the output suddenly shoots up. But what happens later if I keep on increasing the frequency? Will the output keep on going down or will it go up again sometime? Any idea? If this were a sinusoidal source, then then the response is well known, right? The response is like this. Zero response at low frequency, high response at omega zero, and again zero response at very high frequency. And there's only a single peak, right? At omega zero, if you're using angular frequency, or f0 if you're using ordinary frequency. My question is, and here it's sort of obvious that as you keep on changing your source frequency, you will see a peak when source frequency matches omega zero, and then when you go away from omega zero, you will see the thing drop. Do you expect the same thing to happen here? You should be able to tell me from whatever is written on the screen right now. Yes? Anybody? It should peak at 1/3 omega 0. Yeah, the point is when you get close to 400 hertz, what is going to happen is that the 3 omega component is actually going to come to resonance again. Because when your input is 400 hertz as a square wave, that actually has a 1200 hertz sine wave in it, whose amplitude actually is 1/3 the amplitude of the original 1200 hertz sine wave. So you will again see a peak. Okay. This peak will be smaller in size than the original peak. How much smaller? That's sort of obvious. It will be 1/3 the size of the original peak. When you get to 240 hertz, you're again going to get a peak. And this peak is going to be roughly 1/5 the size of the original peak. So basically the output is going to go up first at 1200 hertz, it reaches a maximum, then goes down, stays down until you reach 240 hertz, sorry, until you reach 400 hertz, that's the 1/3. Here I'm decreasing the frequency. If you keep on increasing the frequency, the output will keep on going down forever. But if you keep on decreasing the frequency from 1200 hertz, each time you reach one of the odd harmonics, or each time one of the odd harmonics has a frequency of 1200 hertz, you are going to get a peak. Now, if this were all there is to it, then you would not need a computer to tell you the answer. You could immediately tell me the frequencies at which the peak will be reached. And in fact, you can also tell me exactly how big the peaks will be, right? For example, at 100 hertz, will you get a peak? Yes or no? Okay, Shomo is saying no. Okay, but why not?
Sir, it's not the 1200 is not a odd multiple of 100, right?
Right. So since the square wave only has odd harmonics, if you put in 100 hertz input, you will get 1100, you will get 300 hertz sine waves, but you will not get 1200, so you will not get a peak. Fine. But suppose you put in 1200 hertz by 15 as the input, you will get a sine wave, or you will get a peak. But what will the peak look like now? Can anybody tell me? That is, if I put in the input frequency, let's so I put in 80 hertz, then 1200 hertz is the 15th harmonic, right? Actually, it's not the 15th in this. It's actually only the 8th. But anyway, it's the 15th harmonic, counting all the missing ones as well. So you expect a peak. But what will the output look like? Will it look like a sinusoid? And what will its frequency be? Okay, let's ask a simpler question. When I put in a 400 hertz square wave, what will the output look like? Will it look like a sine wave, and what will its frequency be? If f is 400 hertz, we have just decided that it must peak. But what will the output look like? Will it look like a sine? And if it does, what will the frequency look like? Yes? Okay, let me give you part of the answer. At 400 hertz, the output will look like a sinusoid. But what will the frequency be? Sinusoid of what frequency? This is such a simple question that I'm feeling a bit worried as to whether I'm at all being heard at all or not. My screen shows that I'm connected, but yes? Come on. The 400 Hertz input, it has a 400 Hertz term, there's a 1200 Hertz term, it also has a 2000 Hertz term, and also higher frequency terms. Now, why did we expect there to be a peak? Because the 1200 Hertz term, which is in the input, that's close to resonance, right? So this one which is far away from resonance and this one which is far away from resonance will be suppressed quite a lot. So you will effectively see only this output, which is why we said the output peak will be only 1/3 as high as the original peak that you saw. Okay? And what will the frequency of the output be? That's obvious. It's going to be this 1200 Hertz because that's the only one which you're seeing. You're suppressing the others. Is that okay with everybody? Please let me know if this is not intelligible.
So I have a bit of confusion with the circuit itself.
Yeah.
So like I can understand this, but the point is when we are talking about the parallel resonance circuit,
Yeah.
the impedances of the capacitors and the inductor, we know that to be j omega c and 1 over j omega c and j omega l for a particular value of the frequency. But given a square wave coming, so what omega are we taking to be the
that is the whole point. These expressions 1 by j omega c, j omega l, etc., all make sense only for a particular frequency sinusoid, not just a frequency. It only makes sense for sinusoidal inputs. Because where did they come from? If you just remember, the basic idea was that the voltage drop across an inductance is going to be L di dt, right? So if I is I0 e to the j omega t, which by the way is of course wrong in the sense that current is never complex, but we know what this means. We know that this means that we have to take the real part to be the actual current. That much is fine. But the real part is a cosine, right? Or cosine omega t plus phi, where phi is the phase of I0. Right? So this form only works for sinusoids, not for anything else. And this expression, once you plug this in, di dt becomes very simple because when you're differentiating an exponential, all that happens is j omega comes down, and then you are left with j omega l I0 e to the j omega t. This, of course, is the current. So the voltage across the inductance is j omega l times the current. Right? And that's why we say that the impedance of the inductance is given by j omega l. Just like Ohm's law. Voltage is impedance times current. However, and this is there is a reason behind the particular problem. This works only for sinusoids and for nothing else. For square waves, you cannot take a definite impedance. It doesn't make sense. Okay? And that is why what you have to do is think of the square wave as made up of many, many sinusoids. This is just a sum of lot of sinusoids which are going in, and because your circuit is linear, you can find out the output for each of the sinusoids separately and add up the result. Okay? So sine omega t is a sinusoid. There's no problem with that. If you had sine omega t alone, you would get a response which the formula that we had calculated will give you. Sine 3 omega t by 3 is also a sinusoid. For that, you will also get a response. Okay? So you have to keep on adding individual outputs. And the reason why you can do that is because your circuit is a linear circuit. So when you give it a sum of lots of inputs, the output is the sum of the corresponding outputs. By the way, this is the reason why Fourier series is so important in physics. any periodic function can be written down in terms of sinusoids, and sinusoids are very easy to handle in most situations. The reason why we are dealing with sinusoidal inputs is not because, and the reason why all AC that you have ever seen, in most situations you will have expressions like A sin omega t. The reason behind that is not that all signals are sinusoids, but because all periodic signals can be written in terms of sinusoids, and because sinusoids are easy to deal with as far as calculus is concerned. Okay. Now, coming back to the original question that I asked, not the original, but the question I asked a while ago. If you put in 80 hertz, then the 15th harmonic is 1200 hertz. So that alone, if that had been the only thing you would see at your output, you would see a sine wave whose amplitude would have been 1/15th the amplitude of the original signal. That's simply because of the 1/3, 1/5, 1/7, these coefficients which are specific for the square wave, and whose frequency would have been what? For an 80 hertz input signal, what would the output frequency be? 1200 hertz again, because that's the one which is being picked up, right? That's the only one which is substantially transmitted by this circuit. The rest are going to be blocked or suppressed. However, the important thing is, if 80 hertz is your input, then the 15th harmonic is 1200. The 17th harmonic is 1360. Okay? And the 13th harmonic, what is that? That's simply 160 hertz less, right? 1040 hertz. Now, compare the situation with when you had 400 hertz as an input. When you had 400 hertz as the input, the resonant frequency was a third harmonic, which was 1200 hertz. And what you had was 1200, 400, and 2000. 400 and 2000 are very far away from 1200, right? So they were suppressed a lot. Whereas 1360 and 1040 will be suppressed, but will not be suppressed completely. That is, they will not give you negligible inputs. So what you will see is actually almost a 1200 hertz sinusoid, but with 1360 hertz slightly and 1040 hertz slightly mixed in. So what you will see is not a sinusoid. I will not even try to draw it, but you will see something like peaks and troughs in the sinusoid. Standard beats which come in when you have frequencies which are close by superposed. So for higher harmonics, that is, when your input frequency is low and you are only getting resonance from very high harmonics, the nearby harmonics are not far enough away to be suppressed completely. So you will get an output. So basically what you are supposed to do is sum up the output for each of these individual terms. And frankly, although this is an infinite sum, you only have to sum up over the first few, not very many. Now this is something you have to decide how many terms you will sum up and so on. And then your result will follow from there. So any questions about this? Is this circuit used as a waveform converter for practical applications? Well, not really. This circuit is used primarily. This has many practical applications. This major practical application is as a tuner. Say radio tuners, television tuners. All of these have to deal with lots of input frequencies, right? Radios. All the radio stations essentially transmit at different frequencies. So if your radio or if your television actually amplified all of those, and you got to hear all of them together, then the whole thing would be a disaster. You would not be able to pick out anything. The tuner essentially picks out a range of frequencies close to the resonant frequency, and that is what you get to use it for. These are used for tuned amplifiers. These are used in conjunction with amplifiers basically to pick out certain frequency ranges. That's one major application. But there is another major application of this particular circuit, which is actually exactly what that problem says. It's used in the lab for determining Fourier series. You understand what this does really, right? Because as you keep on tuning the frequency, you'll find a peak at 1200 hertz, let's say. Then another peak at 1/3 the height at 400. Then another peak at 1/5 the height at 240, and so on. So this way you can figure out what harmonics are actually there and what are their relative amplitudes. So in the lab, this particular setup is actually used. This not only this particular setup, the problem that I gave you essentially is a standard lab problem. In the lab, we call this determination of Fourier series, but it basically is using a parallel resonance circuit to pick out different resonance frequencies. But in this context, let me ask everybody a rather obvious thing, but it's still something which requires a bit of thought. When you say Fourier series, what you usually mean is I put in a frequency f and I get various multiples of f, right? And with different amplitudes. Like here, I put in omega, I get 3 omega, 5 omega with amplitudes of 1/3, 1/5, and so on. The way this experiment is done is actually quite different. You don't give in a particular square wave, you give square waves of different frequencies and then check where you get resonances. So instead of putting in 1200 and detecting outputs at 1200, 3600, 6000, and so on, what you do is put in 200, 1200, you get a peak. Then you put in 400, or actually you keep on changing the frequency until you get a peak. The peak will happen at 400. And then you will get 1/3 of the amplitude. So this is done in quite a different way from what the Fourier series expects us to believe. The Fourier series essentially says, you give me a frequency omega for a periodic wave, I will give you all the harmonics. Here what you're doing is you are actually changing the frequency of the input and just picking up the resonances. What was the question, Ritik? Sorry, let me just read that. What will be the final waveform for a particular frequency of a square wave? That exactly was the problem. Find out. That was what the question was about. If your frequency is very close to a sine wave, close to a resonance, then it will be almost a sine wave of 1200 hertz. But the real question is, when you are away from that, what kind of output you are going to get? It's up to you to figure that out. It's a pretty simple series summation problem. So I will not give you the answer to that question because that is exactly what is asked in that problem. So work it out. If you have not worked out the problem yet, do it. The question that I had for you is, why do we do it this way? Instead of keeping the frequency of the input fixed and figuring out resonances, figuring out from different frequency resonances what the outputs are going to, what the output is like. That is, instead of if you could give this frequency to a resonance circuit with a resonance frequency of 1200 hertz, then you could give it to another one with 3600 hertz, then you could give it to another one with 5000 hertz and measure the various responses. Instead of that, you're actually changing the input frequency. Why are you doing that? Is the question clear?
So can you say it again?
Sorry, could you just repeat that? Because I heard a lot of static.
Can you repeat the question?
The question is, we usually call this experiment, when it's done in the lab, determination of the Fourier spectrum. But the Fourier series looks like this, right? For a square wave, you give it a particular omega, it has omega, 3 omega, 5 omega, etc. So the natural thing, if you wanted to determine a Fourier spectrum, the natural thing to do, I expect, would be give a particular square wave, use a resonance circuit with different resonance frequencies, and change that resonance frequency and cross check. Okay, you get my point? That is, if I have, for example, I can easily tune the resonance frequency of this circuit by changing, say, the capacitor. If the capacitor had been a variable capacitor, I could keep on changing the resonance frequency and see that where I get the resonances. I should theoretically get a resonance at 1200, then 3600, then 6000, and so on. Instead of that, what we do is we change the frequency of the input signal. Why do we do it? Okay, think about it. I'm going to ask this again the next day. This has
Sir, maybe the
everything
quality factor changes.
good. That would be a very important point actually.
To reduce attenuation.
Well, I would just put it this way. A fixed resonance circuit has properties which are well defined. As was said right now, the quality factor is one property, but more importantly, if you keep the R, L, and C fixed, then it has a well defined transmission probability, right? Or transmission fractions. So checking with that while changing your source frequency actually gives you a much more stable output. Your circuit may not work very well at high frequencies. Say an inductor might end up having a pretty high resistance, not just inductance, very high resistance at high frequencies. Can anybody tell me why? Why do you expect an inductor to have a high resistance at high frequencies? I mean resistance, not inductance. Or not impedance. I'm pretty sure you have studied this in some class so far. Have you heard of the skin effect? When high frequency signals travel through a metal, they do not go in very much. They actually travel mostly in a narrow region very close to the surface. As a result, what happens is that the effective cross section of your wire goes down. So for high frequencies, the wire essentially looks like a very, very thin wire. Not even if you have a thick wire, the core is almost untouched. The current doesn't flow through the core. It flows essentially through the surface. There is a standard electromagnetic effect. And so for high frequencies, the impedance, the inductance will actually behave like a rather large resistance also on top of its impedance. So its behavior will change. So if you keep on changing the resonance frequency by keep on changing the circuit, you will run the risk that your circuit will actually behave differently at different frequencies. It's much easier to control the source frequency rather than control this resonance frequency. It's just a matter of practical convenience, nothing else. Okay, there was one question which was asked to me in my mail. Let me repeat once again. If you have a question about the course, it's best to actually ask it either in the discussion forum or in these classes so that everybody can benefit from the answer. Okay, I will just tell you what the question was. The question was simply this. We found out that the power for an AC circuit is given by this. There's a half or no half depending on whether you are quoting the VNI using amplitudes or RMS values. Here I'm assuming RMS values. Now the question simply was this. The RE here ensures that this is real. But the real part of a complex number might very well be negative, right? So what would negative power really mean? That was the question. By the way, for a resistance, the power is I square R. That of course is always positive. Now this positive power, does it mean that the resistance is a source of power or a sink of power? Does it provide power or does it dissipate it? It's a sink, right? So it dissipates. A resistance takes away energy, away power. So when you get a positive power at the end of a calculation, it means that it's actually a sink. It takes away power. On the other hand, if the power at the end of the calculation came out to be negative, it would mean that that object is actually acting as a source of power. Okay. Either because there is a power source actually inside it, or might be because it's converting power. So like in an amplifier, it can convert power which is coming from a DC supply and changing that into a signal. Let me just point out one thing. V is, suppose I am talking about a particular impedance, some Z. It could be an inductance, could be capacitance, could be something else. Could be resistance, could be some combination. So V will be Z times I, right? So the power is actually real part of Z times I mod square. So it's real, ultimately real part of Z times I mod square. I mod square, of course, is a positive number. So the only way in which power can be negative is if the real part of your impedance, which is the resistive part of your impedance, turned out to be negative. A negative impedance essentially, not a negative impedance, but a negative resistance, essentially is a source of energy. A device in which current actually flows not from higher potential to lower potential, but from lower to higher. So that's exactly what a negative power would mean. We will see examples of that later on. In most cases, that would be either because you have a source of power inside your object, or because your object is effectively producing power by changing DC power into something else. And you are only looking at the AC power, perhaps. We will see examples of this several times in the course. Okay, I will stop taking questions now, simply because I want to talk about one thing in particular, which is about solving equations on a computer. So I'm asking this specifically to the BSMS students. You have just completed a computation course almost immediately before this course, right? It was in the end of summer this time. So what did you learn about solving differential equations there?
We didn't learn about differential equations in the course.
What? Sorry, I couldn't hear you.
We did not learn about how to solve differential
Okay,
equations.
you didn't learn about how to solve differential equations in the course. Fine. So I will just illustrate one method of solving this. I'm not going to talk about how to solve differential equations or what the algorithms are, because that is not really what this subject is, this course is about. And anyway, next semester you're going to get a rather detailed course on that. That is computational physics course. A major part of that will be solving differential equations. But let me just tell you one way to do this using the scipy package, which Python has. Even if you are not familiar with Python, it should not be very difficult for you to follow this. So let me just give you this example. Let's say we want to solve this equation. Okay. So what kind of a differential equation is this?
Non-homogeneous second order ODE.
Okay. Second order is what I'm really interested in. The rest is also important. But as far as we are concerned, we are going to basically use a particular, okay, you have been exposed to the scipy module, right? This one?
Yes, sir.
Okay. At least those of you who have done this course. I know that there are students here who are not from that course, but most of you have done this. And frankly, even for those of you who haven't, it's not really a big deal. It's pretty easy to pick up. And in case you don't want to use NumPy and scipy, you want to use your own programming language, feel free to do it. But anyway, scipy is the module of Python which has many things, including methods for solving ODEs. But one important thing is it can only handle one-dimensional or first order ODEs. This is not a first order ODE, right? This is a second order ODE. So how do you handle that? You handle that pretty simply by making this into a first order ODE, not one first order ODE, but a bunch of coupled first order ODEs. You just say x dot equals v. Okay, this let me change this to f sine omega t because I don't want this v0 to be confused with this v. X dot equal to v and v dot equal to minus kx plus f sine omega t. Okay. So let's say we want to solve this set of equations and we want to do this for, say, k equal to 1, f equal to 1, omega equal to 1. Let's keep things simple for ourselves. Giving these parameters is no big deal, but you should be able to do it yourself. Now, let me show you how you would solve this using scipy. Okay, this should be pretty easy to see, right? You can all see this?
Yes, sir.
Now, it would have been great if I had a program written down, okay? But I don't. So I will have to risk typing out the program in front of you and making a mess, possibly, but let's just see. The basic idea is the first thing that you need to do is import some obvious candidates. You need to import NumPy because you want to use NumPy arrays. This is a standard mantra which people use basically because you don't want to keep on calling everything NumPy dot something, NumPy dot that. You just say import NumPy as NP. Henceforth, you can just use NP as a name for NumPy. Well, the other thing, I need to import the integrate submodule from the scipy module. And that's a pretty big mouthful. So what I will do is import this as SI. Then that name, SI or NP, these are just conventions. You could use anything else, but most people use these. And just because I want to also see the output, I will import pyplot submodule from matplotlib. That's going to allow us to draw graphs from within the program itself. Okay, just tell me one thing. In your course, did you actually see matplotlib being used? This one? Yeah.
Yes, sir.
Yes, sir.
Yes. Okay, good. Fine. So at least this much. Now let me do one thing first. If you want to know how to use scipy.integrate, you would need to know what function in scipy.integrate to use. That, of course, is knowledge that cannot be deduced. You need to know it. I know the answer, so let me tell you what the answer is. There are actually several ways of integrating differential equations in scipy. One of them, the one we are going to use, is called odeint. ODEINT. Now, what to do, how to use odeint? The answer is you have to look up the documentation. No other way, really. Of course, if you have a wonderful memory, you can memorize everything about how to use a particular function, but that is almost impossible, so let's not even try. So what I'm going to do is just look up Google, and this is the standard first page that you get when you just type scipy odeint in Google. In fact, if you had forgotten odeint, you could have just asked Google how to solve differential equations in scipy. It would have told you scipy odeint, and this is the page. Now, this is a huge page. and it has lots and lots of details. So if you really want to become an expert in this, you have to read the whole thing and understand every step. But for us, what is important is basically the top line. It says scipy.integrate.odeint. That's how you call it. By the way, we are not going to call it this. We are going to just say si.odeint, because for us, scipy.integrate has been abbreviated to si. That was the import command. Then si.odeint followed by some arguments. Now I don't really need this many. I need to focus just on these three. The rest are details. We don't need to worry about them right now. Anybody who is interested, just read up the documentation. It's pretty easy to read and understand. Now, what is important is dy dt equal to function of y comma t. That is what is being solved here. So func is nothing but the function which gives you the derivative. Okay, but this is important, y comma t. So the dependent variable y comes first, then comes t. Okay, and where y can be a vector, this is just another way of saying y can have more than one element in it, more than one component in it. So let's see how we would do this. I would need to define my derivative function. So let's define it. This is how you do it in Python. You just use a def keyword, then you give it a name. Let's say derivative or derivative. This is just a name that I've given. And first will be my capital X, which is now, notice that that I have two variables here, small x and small v. So capital X basically is this. It's an array which contains both x and v in it. So capital X and t, that's. So how would I define this? I would just first take capital X, which has x and v in it, break it up into small x and small v. This is standard unpacking. Capital X has two numbers in it. Small x the first number goes in small x, the second number goes in small v. And then I'm just using names which should be sort of obvious to understand. Dx dt equal to v, dy underscore dt. So what will this be? This will simply be minus x plus what? Anybody tell me what to type here? Our equation was, okay, let me just show you what the equation was. This was the equation. So what I've done is I've found this is the derivative for x, this is the derivative for y. And this is the formula for the derivative for, sorry, I shouldn't really call it y, I should call it dv dt. The name doesn't matter, but it should be named in a way in which you can understand why you were calling it that. So that's dv dt equals what? So tell me what I should type here. And chatting, unfortunately, doesn't really help much because I can't see your chat. Now, okay, Shomakandi Shah is saying you did scipy.integrate in CS2201. That's what I was asking. But did you do solving differential equations using that?
No, we just did numerical integration.
Numerical. So integrate has many things. Among them, that's what I expected, that you did numerical integration. But this one actually also solves differential equations for you. Okay. So what I really should, as Shomo has already said, I can't just say sine t, I have to say np dot sine of t. Simply because that's sine taken from the numpy module. And then I need to return these two quantities, the dx dt and dv dt, in that order. Remember, x and v were in that order in your capital X. So the output should be in this order. I need to pack them in an array, numpy array, and return this. Done. So your function deriv is done. And now what you need to do is, Oh, sorry, this will give you an error. I should say si.odeint because I've already abbreviated that. Deriv. Now, I don't know about people, but I can't remember what order the things go in, so I have to look up. The functions which gives the derivatives go first, then y0 goes in, that is the initial value, then t goes in. T is an array of t values, of the values for the dependent variable where you want the answer. So first of all, let's produce a t. Again, simple numpy function which will do the job for me, but you can also do it using many other methods. Say 10,000 points between 0 and 100 equally spaced. Those are the t's for which I need the answer. Y0 is the initial value. In this case, we can of course call it x0. That's an array which has the initial value of x and the value of y. So initial value of x is 1. Let's say that's just just an initial value which I've given. Let's say 1 and 0. And then what I need to do is call the odeint with just these. The derivative, then x0, then t's. And I'm done. The program has actually solved the differential equation for you. 10,000 points, 10,000 values of x, 10,000 values of y. So these are the huge arrays which you have. If you look at the shape of the array, you will see 10,000 rows with 2 columns. Roughly, in the matrix language, that's what it will look like. The first column, of course, is the x, second column is y. So just to see how this works. Now I want to plot just the x. That means I want to plot the first column. What will I do? How can I extract just the first column from this array? First column, remember, is column number 0.
Zeroth index.
What?
Within third brackets, we have to put 0.
Well, 0 will just give you this. What you want is this. You have to say, you have to give both indices, I and j. You have to say j is 0, and for I you give this. There's an empty slice, which means takes the whole thing. So this takes the entire call. This gives all the values of I, and j is fixed at 0. So that's one line, and if I want the v as well, that's another line. These are 2 graphs which are ready to be plotted, but unless you use plt.show, you're not going to be able to see them. But this is what plt.show shows you. Okay? So this is the output, the solution to the differential equation, both x and v. By default, the blue color is the first one, the orange is the second one. Okay, the details you can always look up on Google. But this is basically how you solve differential equations using odeint. The basic idea is simply this. Have a function which will calculate the derivatives for you. If there's more than one variable, all the derivatives one after the other has to be calculated and packed in an array. Then you have an initial condition array. An array which has one value for each variable. Then you have the values of t at which you need your solution. Just basically this one line will calculate the solution for you using a pretty nice, decent algorithm. What algorithm it is, we are going to talk about later in next semester's course. Okay. Okay, before I go, I just have one announcement, which is this Monday I have an important meeting, so I will not be able to take the 9 o'clock class. But that means that I'm going to take the class on Tuesday. I will send a mail, but let me just state it right now that my class will be on Tuesday. for next week and next week only. Tuesday and Thursday, of course. And we are going to discuss diodes in the Tuesday class. The video is already up. There will be one more on diodes. We'll discuss those. Okay, bye for now.